All right, we are back. It is Wednesday, November 18th, starting chapter 13. One topic to wrap up in chapter 12, I think the Sharpless epoxidation we didn't cover, but we'll do that. 13 is the beginning of spectroscopy, so we'll take a break from reactions. No reactions, the next two chapters, yay! Usually there's a lot of cheering at that point, okay? Muted applause today, that's okay. Homework 13, we will finish it in a couple of class periods. So Friday, homework for 13 will be due. Start chapter 14, which is the big one for spectroscopy, NMR, nuclear magnetic resonance. So that's coming up. Test 3 wrapped up well. Sorry it took us a little longer to grade, but we did get it done. And there was another 100. Congratulations. Very good. There were a number of high scores in the 90s. The average dipped down a little bit to 72, but that's not bad. That's very good for a tougher test like this with a lot of reactions. So don't worry about that. If you're below here, don't despair. We still have what, midterm 4 and the final. So there's 300 more points to go for this class. The points are definitely backloaded, so it rewards those students who really persevere, keep studying hard, and even though we've covered almost all the material, we still have about half of the points still to go. So that will really reward you to hang in there, though. There were a number of people who turned around their score relative to test 2. I think there were a couple who turned around by 15 or 16 points, which is impressive there. So it can be done. Okay, adjust the amount of time you need to do, and you can get that done. All right, what do we see up here on the overhead? We see a molecule jiggling around, ethylene or ethene, and this is in the IR. This is a what? A bending of those bond angles. So that's a bending mode. So it's absorbing radiation in the infrared range, and it's bending or perturbing those bond angles there. So normally that's 120, but you can see it's compressing and elongating there. That's that vibration here at 1496. I don't know if you can see the unit there. We'll talk about IR and get the units there. We can also increase the frequency, and now we're looking at bond stretches. We're elongating the bond length. And those are the two different modes of vibration, bending the theta bond angle and elongating the bond length. And that's a sympathetic vibration depending on the frequency of the electromagnetic radiation. So this is, again, your old friend ChemTube here. If you go under structure bonding and molecular vibrations, it'll give you some examples here to do. I think benzene's in here too. Benzene's a good one to look at. Let's see if that pops up. Okay, yeah, there it is. And then you can look at the frequencies here, frequency list. And if you're down low here, you can look at, again, bond angle, bends or deformations there. Let's find another one. Okay, so that's an out of plane bending mode. Let's see one in plane. Oh, there we go. There's an in plane bond angle bending mode that's going on at a specific frequency. And let's see if we can find a bond length one. Oh, there's one. Yeah, there's a bunch of different ones here, these simulations here. You see the bond lengths being compressed and elongated? That's at a specific frequency, okay? These are sympathetic or harmonic oscillations. Molecular dynamics of the molecule based on the frequency of the electromagnetic radiation. But that's a way to figure out what we've got molecule-wise. But we'll get into the details of that here after we finish a little bit on the Sharpless epoxidation. And this is from chapter 12, right? We left off with this. In fact, you had one homework problem for homework 12 that you had to do. But you could see what the product was. And like I told you, you don't need to know which enantiomer is formed from which enantiomeric form of the catalyst. If you want to make an enantiomeric epoxide, just use one of the Sharpless combinations. And these are these diethyl tartrate catalysts. Diethyl tartrate complex with titanium here. That's actually the full catalyst. The stoichiometric oxidant is tert-butyl hydrogen peroxide. So it's another peroxide reagent, just like MCPBA was a peroxy acid we saw for epoxidation before. It's really specific for allyl alcohols. You have to have an alcohol here. That has to coordinate the titanium. I'll show you a little bit of the mechanism here. But if you could coordinate the alcohol with the alkene, you can epoxidize either this enantiomeric form and 95% enantiomeric excess. That's almost pure that enantiomer, okay? And if you use the opposite tartrate, the L form here, I'm sorry, this is the dextrorotatory form. This is the L referring to the stereocenter. Don't get confused by that. So this is the minus form. This is the plus form. This goes to the opposite enantiomer and high enantiomeric excess. So you can make either one. Like I said, for the purpose of this class, don't memorize whether plus gives that type of enantiomer or minus gives that type of enantiomer. You can just do either one. The mechanism's reasonably well known. It's quite complicated. It has to do with how the allyl alcohol bonds to the titanium tartrate complex. E stands for esters coming off the tartrate. This is diethyl tartaric acid ester. It has two stereocenters, and that creates two chiral pockets, we say, where the allyl alcohol can only fit in one form there. And then the peroxy is delivered from one face to give that enantiomer of that. And to show you how it's useful, there's a couple examples from the book. Here's an allyl alcohol with an alkene and an alcohol. That's what allyl alcohol means. This form with the plus diethyl tartrate gives that enantiomer in highly pure form. And you can have more complex allyl alcohols. You have to have an alkene there, of course. Tetrasubstitute alkene, very high enantioselectivity for that enantiomer. See, these are enantiomeric forms, both of these here. Very useful reagent. He won the Nobel Prize because it was the first catalytic asymmetric reaction where you could get either enantiomeric form of the products. Okay, so yeah, there's a little way to remember which one goes to which, but you don't need to do that for this class. I like this example. This is the pheromone of the gypsy moth. This will attract moths from all over, from miles around. It's one of the most sensitive insect pheromones known. And it's chiral. It's got this epoxide here. It's a cis epoxide, but two different groups on the two sides. So that is an enantiomeric form. The plus form is the one that attracts the moths. And it's made using the Sharpless asymmetric epoxidation, that enantiomeric form. There's a few more steps here to convert this alcohol into this chain here. That can be done. And then that natural product attracts those gypsy moths just as well as the naturally occurring pheromone. So the power of synthesis, yeah, you can attract the bugs there. I think that's all we need to say. Any questions about that? Yeah, don't memorize which diethyl tartrate goes to which. If you need to do it on a quiz or a test, just show one form, okay? Say the plus DET or the minus DET. And I think that'll be good enough. Okay, let's move on to what do we need to do now? Oh, give the outline for chapter 13. Mass spectrometry and IR spectroscopy. We've got some terms here to learn and what's going on. So we've appreciated your patience all along. The first part of the semester, we've given you a lot of isomers and a lot of structures, and you've just taken our word for it. You've assumed we know what we're talking about. That has to be the structure. That has to be the structure. Okay, now we're going to arm you with enough information to determine how we know what we've got, okay? What isomer is it? Which one is it? Especially combined with NMR, you'll be able to nail these things down. But you learn a lot with mass spec and IR. Mass spec here, we take the molecular ion, which is generated in the mass spectrometer machine. We ionize it, we knock out an electron, and we form a radical cation. That's what you actually observe. That's called the parent ion, okay? And what actually is measured here is the mass to charge ratio. This is the M to Z thing here. This is the actual information we get out. We're not actually absorbing electromagnetic radiation here. We're ionizing the molecule, having it fly down a vacuum tube and hit a detector. Because it's positively charged, it'll hit the detector plate which is the cathode part of the circuit, which is negatively charged. And that electrostatic interaction is very powerful. And it'll hit that detector plate with a certain impact based on how heavy it is. And so with the computer, we can figure out how heavy that ion is hitting the detector plate. Obviously, there's a lot of electronics to it. I'll show you the basics of it. But what we get is the molecular weight, and we can see isotopes, okay? We're going to get the masses of the actual isotopes, not a weighted average. We're going to see the actual isotopes, okay, which is can be powerful. It'll also fragment. This is a high energy ionization event here. It'll be an electron beam, which has many hundreds of kcals per mole in energy, which often fragments the molecule apart. But we can still see the parent ion normally. We can see all the other ions. We only see ions. The base peak is defined as the biggest peak. That's usually the most stable cation. Usually it's not the molecular ion, it's often the major fragment, okay? The nitrogen rule means that if it has 1 or 3 or 5 nitrogens, it'll have an odd mass, the molecular ion. If it has an even number of nitrogens, it'll have an even mass, okay? And if it has 1 nitrogen, the molecular or parent ion will be odd, like I said, and all the fragments will be even. Now, if it just has carbon, hydrogen, and oxygen, the parent ion will be even and all the fragments will be odd. So you can kind of tell a lot there. And because we're seeing isotopes, we can see halogen isotopes, chlorine 35 and chlorine 37 at a ratio of 3 to 1. That's the natural abundance. So up there, if we have an alkyl chloride and we see a 3 to 1 for an M and an M+2 peak, you see the heavier isotope, lower ratio there. That's often diagnostic of halogens. If we see a 1 to 1 parent ion up there, that's bromine, 79 to 81. They have an abundance of 1 to 1. So it can tell a lot about if we've got halogens in there. Fragmentation, I'll show you a little bit about that. I won't emphasize that though, okay? I'll just show you a little bit about it. Types of mass spec, high resolution. It's always in high resolution mode or HRMS, and we can see the exact mass. And I'll show you it here. I've got an example on the board. Gas chromatography, we can separate molecules if we have a mixture first and then shoot each pure peak into the mass spec. Okay, there are other ways to ionize, electrospray, ESI is the more modern thing, or MALDI with laser desorption to do bigger biomolecules, but we'll stick with electron impact or an electron beam ionization or EI mode. And then we'll do IR, which we just showed there with the graphics from Chem351. This is true absorption of electromagnetic radiation. So we're shining photons of specific energy onto the molecule, and they'll absorb in the IR range to excite what? The deformation of bond angles, which is the theta bond angle, or the bond bending, we say, or it can excite the bond lengths. Okay, 2 atoms for a bond length. That's the bond stretching mode. And that depends on functional groups and where they are in the molecule. So this will be diagnostic here. We've got the typical bend range, which is 400 to 1400 inverse centimeters. It's a strange unit. I'll show you about that. It's nu bar, actually, it's called, or 1 over lambda. Lambda and frequency, nu, are inversely proportional, okay, based on this equation, the fundamental equation for electromagnetic radiation energy equals Planck's constant times frequency. Frequency can be defined as what? A speed of light over lambda. So there's all these relationships between those numbers. And hopefully you've had enough physics to appreciate that. I'll review that a little bit. But what you need to know for OChem is specific for different functional groups, okay? Carbon-carbon bonds will resonate around 2900 wave numbers, okay? Carbon-carbon bond, 1460. And that's because it's a heavier atom. The lighter the atom, usually the higher the frequency. Carbon-carbon double bond has a higher bond order, so it's a little bit higher than a single bond. Carbon-carbon triple bond, a little bit higher still, 2200. OH, this is a very diagnostic one. It's very broad, okay? for that bond stretch is 3,500. It really stands out there. You're changing the dipole moment significantly, so it has a large absorption, very broad thing. Aromatic, we saw benzene there a second ago. That's for the CH aromatic stretch. Then we have carbonyls, ketones, aldehydes, esters, amides, around 1,700. Carbon nitrogen double bonds, 1,650, and carbon nitrogen triple bonds, kind of like carbon carbon triple bonds, a little bit higher at 1,250 there. We'll show you some examples of how it's determined there. But here's what we're up against as organic chemists. We can make a lot of molecules, right? We can identify new molecules in nature and other places. We can identify molecules for forensic applications, right? Law enforcement, crime lab stuff, pathology, different compounds causing disease, or toxicology. How do we know what the compound is and where is it though? In synthesis, we need to determine whether our new intermediate or new compound we're making is the right stuff. We always use the combinations of things. NMR, talk more about that, of course. X-ray, we can get the three-dimensional positions of the atoms in a molecule. IR, we can learn a lot about functional groups. You've already gotten a flavor of that. And mass spec, the molecular weight and fragmentation. We have to purify things. We've already talked about a couple of these things here. But this is what we're doing. This enables a lot of powerful things here to create different molecules and to analyze different compounds, right? So here's mass spec. Here's how it works. It's a vacuum tube. Here's our sample. It has to be vaporized. This whole white tube here is a high vacuum tube. Here's the electron beam where the particles come through here and get ionized. And then they're focused a little bit. And then there's a magnet here. And we can change the power of this magnet electronically to focus these ions as they fly down the tube. So the heavier ones won't be deflected as much by the magnet. They'll hit over here. The lighter ones will be deflected more. Then you can just change this and have them hit the detector plate as you vary the magnet. Or you can base it on the time of flight, how long it takes the ions to fly down the tube. That's actually the more modern approach called TOF, time of flight mass spec. This is the older thing, this magnet sector analysis. But we can separate the ions and focus them. The collector plate here, the detector, is a cathode. It's negatively charged. So the cations, as they're formed, will hit that plate. And then what you actually see is just a count of the ions. It always has to be ionized to be hitting the detector. And this just counts it. This is the number of counts here in this axis, and here is just the molecular weight. Okay? So it's not a spectroscopy. It's just counting ions. And let's see the data. Oh, simplest compound. Okay, methane, right? CH4. So here's what it looks like. So the molecular ion has a mass to charge of 16. Where did we get to 16? Well, the atomic mass of carbon is what? 12. Okay, the most abundant one is 12. That's the definition of the atomic mass unit. 1 mole of carbon-12 atoms weighs 12 grams per mole, okay? Not all of them will be that exact, but that's the definition of a mole nowadays, the modern definition. The C12 isotope, the most abundant one of carbon, Avogadro's number of those atoms will weigh 12 grams, okay, for a mole. And then we have the 4 hydrogens, and they're what? 1 atomic mass unit, 1 gram per mole, so it adds up to 16. And there's our M peak. It's the most abundant one. It's also the base peak in this case. We see a tiny little M+1 peak. What's that? That's C13, right? The less abundant isotope, okay? The base is 16, but there's a little bit of 17. And that's what? C13, which has a natural abundance of 1.1%. So oftentimes you see these little heavier isotopes, okay? Very small for methane. And then what are these down here? We need to look at these. These are losing hydrogens, right? So here's our first one. We pass the beam of electrons in there, and we knock an electron out of a bond. If we remove 1 electron, they come off as a pair, and they actually enter the electrical circuit. So those 2 electrons coming off are lost. What we now have is the cation form. If we lose a hydrogen there, it goes down to what? Methyl cation. We've talked about that before. Very high energy species. Okay, it only forms in the gas phase. Can't make it in solution, but here in mass spec, we can make it. It's right there. We lose another hydrogen, we go down to the methylene radical cation. We use another one, we go to the methine cation, and then all the way down to the carbon one, which is at 12. That's very small, okay? So you see them coming off there. These are the fragments, okay? They have to be charged to show up in the mass spec. But the molecular ion is showing up there. Okay, that's a pretty boring molecule. Let's get to an important one. How about something that has a molecular weight of 86? Where do we get this 86? Well, methane or hexane would be a candidate for this, right? We have what, 6 carbons, C6, H14, add them all up. 6 times 12 is what? 72, okay. And then 72 plus 14, does that up to add 86? Yeah, okay. So you can see how those add up. And there's our peak right there. There's the molecular ion. But notice we're fragmenting a lot here and making 57. That's very common in alkane mass spec. That is actually the tert-butyl cation. And we'll see how it can fragment and form that. And then this 43 peak is very common too. That's an isopropyl cation. So let's go to the board here, Colin, and do a couple more on this type of structure. So if we have 86 for our molecular ion, you know, it could be this C6H14, and we'll see there the exact mass if we do it in high resolution mode and go out to the thousandths place, beyond the thousandths place, right? 86.1096 for the exact mass. Now that's because hydrogen doesn't weigh 1 gram per mole exactly. I think it's 1.0096 grams per mole. But C12 is exactly 12 atomic mass units. But if you add it all up, it's this for the exact mass. But you see the 86, that's the low resolution mode. And that's what you'll normally see in most spectra. But we can determine the high res mode, the exact mass, and determine others. So what would C5H10 be? 510. How many units of unsaturation might we have here? Well, we'd have something like this maybe with a double bond, right? Add that up, C5H10. Oh, that's also 86, okay? So, you know, this can be ambiguous in the mass spec. And what about this? C4H6O2 would also be 86, but look, it has a different exact mass, okay? And that's because there's different atoms here in the ratio. And oxygen, the exact mass of that is actually 15.994 or something. AMU, so it's a little bit different. What you see in the periodic table, a couple people glancing up there, that's the weighted averages of all the naturally abundant isotopes. Those are different numbers. What we're looking at here is the masses of the isotopes themselves, okay? So that's the difference there. But you see, what would be a compound of candidate structure here? Well, we'd have C4, the max would be 10. We're down to 6 here. So how many units of unsaturation here? We need 2, right? So something like this maybe would be a candidate here. We've got a ring and a double bond here. Here we just have one double bond, so 1 unit of unsaturation. But this is also 86, this is 86, and so is this, okay? Let's go back to the overhead up here, Colin, and see how these things are gonna fragment. How do we get these other peaks here? Because our base peak now, the biggest one, is actually a fragment. And notice the molecular ion 86, it's even. There's no nitrogens here, okay? Same thing with the ones we just did, no nitrogens, so they're even. And notice all the fragments now are what? Odd. That's that nitrogen rule thing, okay? Here's some other compounds to look at. Pentine, you can add it up there, C5H8. The molecular ion is 68. It typically loses 1 hydrogen here to form the propargyl cation, which is the base peak actually. But you see the molecular ion, 68, is in there for pentine. Pentene, the molecular ion shows up fairly well, 70. Again, it's even, right? And pentane, 72. So you see they're all different, 68, 70, 72. So you can differentiate those easily just based on their molecular weights, right? Let's see. Here's the nitrogen rule to look at: fentanyl, a drug that's kills pain very well. It's only a prescription drug. It can be abused. So 2 nitrogens. So what? Its molecular weight is even. Okay. If you have an odd number of nitrogens, then you have the odd molecular weight. And here it is right here for Demerol. Yeah, a long name there for Demerol. I like the Demerol common name, the generic name. It's a little easier. 247. That's because it has 1 nitrogen. Okay. So you could easily tell those two apart just by mass spec. Okay. 350 versus 247. And if these were known, and if you're looking for these type of compounds in a drug analysis program, you could easily tell those two apart, right? All right, let's look at the isotopes. For halogens, this is the M+2 halide isotopes, like we said. Natural abundance here for chlorine has the 35 and what, the 37. And that 3-to-1 ratio gives you the atomic mass there in the periodic table. What is it there? Can you read that? 35.45. Okay. That's a 3-to-1 ratio of what? The 35 to 37, the heavier isotope. What you see in the mass spec are those individual isotopes for this molecule, isopropyl chloride. And there it is, 3-to-1. Up here, 78 and 80. Okay. And that corresponds to the isopropyl thing. You also see the ionization here, the fragment, and you see here 43. What's 43? Isopropyl cation. Draw that out, okay? It adds up to 43. It's very, very common. You see it down here in the isopropyl bromide. But here our ratio of isotopes is 1-to-1 for what? The 79 and the 81 atomic mass unit bromide isotopes. There they are, 1-to-1 for 122 and 124 for that. So you could easily tell these apart, not only the masses here, but also the ratios, okay? Very diagnostic. All right, let's get to this fragmentation here and how this works. We knock an electron out of a bond to make the radical cation. And, you know, one of these bonds only has 1 electrons in it now, okay? So it is unstable, but it is charged, so it's flying down the tube. Okay. And then it starts to break things off. So if it breaks off just a methyl here and a neutral methyl radical comes off, then you have a new cation. That's at 71. That's not very abundant. What is more common is to lop off a bigger piece here and have a butyl piece that isomerizes to tert-butyl cation. And these things do rearrange in the tube. And why would it go to tert-butyl cation? And there it is at 57. Okay. And then this can also go to an isopropyl cation right here at 43. And then loss of hydrogens give these other smaller peaks that are lighter than that. But I think that's all we need to know. We see an M+1 peak also at 87. That's a C13 isotope. M+1, yeah. Okay. Well, and that's all we need to see there. The graphics in your book shows this as an N-butyl cation. No, this isomerizes to tert-butyl. The primary one is not as stable as the tertiary. And yeah, don't worry about the mechanism of how that works. I won't talk about that, but fragmentation is known. Here's a couple other fragments to be aware of. Ketones fragment by breaking a bond on the side of the carbonyl to give what's called an acylium cation. And that's this 57 peak here. You see the molecular ion right here, 100 for this ketone. It's showing up. And then the major fragment, the base peak, is right there for the acylium ion. And there's our friend isopropyl cation. And where is it? 43? Yeah, very abundant. Okay. So everything we talked about stability-wise, you see in mass spec. This is out of a different book. This goes over fragmentation of alcohols. I'm not going to go through that. But it's fully analyzed here. You can go through and look at these ions and see where they come from. I won't hold you to that. In fact, I'm downplaying fragmentation. Don't worry about it. Okay. The mass spec gives us the molecular weight. It can be combined with chromatography. This is gas chromatography, or GC, where you introduce a sample that has a mixture of compounds. In nature, a cell will have thousands of different organic compounds in it. We often do a purification beforehand to get it down to a manageable amount, 10 or 20 compounds, okay? Doing forensics analysis, looking for different illicit drugs. there'll be a standardized panel that this will be compared to, okay? So crime labs are very good at this kind of thing, and chemistry labs at hospitals are very good at this, determining what pathology may have been caused by what compound. And so a GCMS instrument has a column here, which has an immobile phase, which is usually fine silica gel. You introduce the material here, and there's a vacuum that pulls on the material. It travels through this column, through the silica gel, based on polarity and molecular weight. The lighter, nonpolar things will come through quicker, okay? And as they come through, they're shunted into the mass spec part, ionized, detected, and then the computer looks at the mass spec for each individual compound, which is really cool, very powerful technique. So here it is. This is the GC part, this chromatogram. It's coming out at different times. These are called the retention times. Don't worry about that. But here's where we started the injection. Here's the most volatile one coming out, or the least polar one. And then the mass spec did its thing. So you see the individual mass spectrum for each individual compound, okay? We can determine which is which. Here's one that's often analyzed, right? THC, where's this come from? Tetrahydrocannabinol. What's the illicit source here? Well, it's legal in many states now, right? Marijuana, okay. This is the bad actor. This is the one that causes hallucinations and problems, okay? If you drive under the influence of this, you're going to be arrested and prosecuted. The good compounds out of marijuana are cannabinol and cannabidiol, which have beneficial effects for different things. I'm not getting into that. But here's a molecular ion for THC, which is 314. And there it is. It shows up nicely. You see a lot of isotope peaks here, M+1 and M+2 up here. That's because you'll have a lot of carbons now. It's more likely to have those isotopes. And it fragments. But this fragmentation pattern becomes a fingerprint diagnostic for this compound. So it's easy to determine this. And mass spec is very sensitive. You can get by with just a picogram of material, and that's enough for many, many ions to hit the detector plate. So you don't need much. The sensitivity is very high for mass spec, which is very useful that way. Here's a typical panel from Beckman Coulter showing off their GCMS with 20 different compounds. And look, they're all baseline resolved coming out of the chromatogram. The GC is separating all of those. Their retention times are all different. And what? You can shunt each one of these into your mass spec and nail down the structure, okay? And there's a bunch of them there. You probably, amphetamine, methamphetamine, very similar compounds, but they're separating them. 5 and 6 are baseline resolve there. It's very good, okay? Let's get into IR now. So mass spec, the main thing is molecular weight. Now we're looking at true spectroscopy, electromagnetic radiation. This is a photon traveling through space. So its rate of translation here, or the speed is what? The speed of light. That's always a constant, c, right? The wavelength is what? Peak to peak distance there. That's lambda. And what is the frequency? Well, the frequency is how many peaks or troughs come by the detector or the observer. Frequency is not the same as speed. Speed is how fast this thing's propagating in space. Frequency is how many peaks come by the detector per given time, how many events per second, okay? Hertz values. Okay, make sure you keep that straight. Well, it's not that big of a deal. But yeah, here I emphasize it. The frequency, nu, is number of peaks per second coming by. Lambda is this distance here, and the speed of light is c, okay? But they're inversely related there. Here's the whole shebang of electromagnetic radiation. Here's increasing wavelength, okay, or lambda, and here's increasing frequency. They're inversely proportional, right? They're related to each other through the equation there. We only look at this visible narrow range right here, which is what the purple, infrared, ultraviolet, near the ultraviolet, okay, the visible range, and then down to the red. But we're going to get into the infrared range here for IR. But there are other things here. The more high energy ones are the gamma and X-rays. The low energy ones are radio waves. Now, how does a spectrometer work? This is an organic chemistry class, but I'm teaching you the fundamentals of analytical chemistry now. It's not that hard, okay? You have a source of electromagnetic radiation, h nu, photons, Okay, you can sweep the frequencies or the wavelengths. There's ways to create that radiation. Then you have a prism that's a splitter that splits the signal out. One part of the beam goes through the reference beam. It doesn't have any sample. The other part goes through the sample. Okay, and then the computer, the detector, just measures the difference. Okay, so it's pretty simple, isn't it? So if the sample's absorbing here, you'll see a difference between the reference beam and the sample beam. And the computer just creates that. Okay, so there it is, analytical chemistry in 10 seconds. We just covered it. Any questions about analytical chemistry? That's all it is. Okay. Oh, no, no. Here's the rub, right? Here's the difficulty. So we can use different domains of this radiation to interrogate molecules in different ways and learn different information. We use X-rays to diffract off crystalline structures to get the 3D structure. That's a high energy process. We can use UV visible radiation to do electronic excitation and measure the HOMO-LUMO gap of molecules. Okay. We use IR to look at bond stretches and bends, which are diagnostic of what? Functional groups. Okay. We can use microwave radiation to cook our food. That rotates the water molecules in food, by the way, the magnetron inside your oven there, or whatever. Or we can sweep that frequency and look at dihedral angles. That's the conformational analysis we've talked about way back in chapter 3, I think. Okay. We're not getting into the details of that. It's pretty complicated. Then NMR will actually use radio wave. Shift and splitting and imaging. This is MRI is also based on radio waves. This is the lowest energy thing, ironically, but this gives us the most information. So the high energy stuff blows molecules apart, X-rays. But NMR, radio waves, actually tell us the most about it. Okay, and that's good because you're putting people inside these MRI machines. It better be non-ionizing, low radiation energy. Okay, but it is a nuclear event, which is kind of a bad thing there. Anyway, okay, so here's what it looks like. And we're going to go to the board here in a second, Colin. So let's see. Let's first look at this. So here's what we're looking at here, and this is a typical IR spectrum. So we see a scale here, 4,000 down here to about 400. And this wave number thing, that's kind of a crazy unit. But then you see down here, and anything below 12, that's called the fingerprint region. And that is where what we're deforming bond angles, okay? So that's the bending region. And anything 1200 on up, this is the stretch region. The stretch region is more diagnostic of functional groups. Don't spend too much time down here in the fingerprint region or the bend region. That tends to have a lot of coupled, very similar frequencies, and it can be difficult to distinguish those. But it can be diagnostic for a known compound. It'll have the same fingerprint output, okay, if it's down here in this region. But what you see right away is an OH group and a CH group. So Colin, let's go to the board here and look at a couple things we need to know about IR. And we'll go back to the overheads here in just a second, but let's talk about a couple things, in particular this unit. Okay, so before the unit for IR used to be this, 2.5 to 25 micrometers or microns. And that's an inverse scale, okay? The energy is inversely related to wavelength. And that lambda value is an archaic one. Sometimes you see micron units. What we do now is nu bar, it's called, and this nu bar is equal to 1 over lambda. And the units here, if you do it, are now centimeters inverse. So to the -1 means that the distance unit is in the denominator. And 1 over lambda actually has the units of inverse centimeters. But that seems kind of like a funny unit for energy. But that is an energy unit because that's directly proportional to the frequency and the speed of light, which is a constant. And then we have this here. This is also proportional through some sort of K to a to Hooke's law, where we have a stiffness factor for the bond over the mass, okay? So if we have lower masses here for XY here, if this is a reduced mass, this will actually be at a higher frequency. Okay, so this is Hooke's law, and that's a harmonic oscillator, right? If we put the bond stretch mode into what we're talking about there, we can see it is related like Hooke's law. It's the square root of this, but this has to do with the bond, how stiff the bond is. Okay, this K is a proportionality constant, which is I think 1/2 times pi. Some other factor, but that's a constant here to relate this to the energy unit that we actually see there. So yeah, so this stretching idea is 4,000 down to about 1,200, okay? And there we're talking about what the bond lengths being stretched, okay? And that's just as we oscillate, what? That 2-atom event, okay? The bond length. Now, when we go down here, 1,200 down to 400 or so, okay, this region here is the bend region, and that takes less energy. You see, the nice thing about inverse wave centimeters now, it's directly proportional. High energy here on the left, low energy here on the right, and that's a bend deforming what the theta angle, which is an X, Y, Z type event, where we're deforming this, right? This is the theta. This is different bend-wise than the stretch, which is the bond length. Okay, this is higher energy. But this is more diagnostic for the functional groups. Okay, so let's look through it here and see what we need to know. Yeah, there's an alcohol. We see a CH around 3,000, and we see this big OH absorbing here. Now that's the OH stretch, right? And that's because it's hydrogen bound, and as that bond oscillates, gets bigger and shorter, it's changing the dipole moment. So we have a large region here, and it absorbs almost all of it. This is in percent transmission mode, so if it's 100% transmission, nothing's absorbing at that frequency. And again, this is a sympathetic vibration, so nothing's being absorbed here, but when it gets to this frequency, what? It's activating that bond length to vibrate, okay? So it's always a sympathetic response to the applied electromagnetic radiation. And then the CH there. So here it is. The higher energy things are down here, the lighter elements, okay? And then things that are triply bonded, and then doubly bonded, and then singly bonded that are heavier. And that should make some sense energy-wise, and by Hooke's law, that equation up there. So let's look at some specific ones here. So there's a ketone and an ester, okay? So we have CH groups all over the place, and we have a carbonyl, which is sharp, but it absorbs a lot. And that's typically around 1,700, very diagnostic for carbonyl. So know the frequency for a carbonyl. That's one you should memorize. And know the one for an alcohol, 3,500. So I'll give you a few that I want you to know. And by focusing on those, you'll figure out most functional groups right away. But look, the fingerprint regions are really complicated. We're going to stay out of that region, okay? The ester is similar there, about 1,700. So you really can't tell these two apart. They're very similar there, okay? Have to go to mass spec to figure those out. So here's the ones you need to know. OH. NH is similar. Don't worry about that. It's not as electronegative as oxygen, so it's not as strong. Dipole moment's not as strong. But look, hybridization changes things, right? If this is sp hybridized, it's higher, right? sp3, okay? Lower S character, that's at a lower frequency, okay? Same thing with triple bonds here, higher frequencies compared to double bonds. And then aromatic, there's some unique things here with that. I'm not going to go into that. Let's see, you can tell an alkane from an alkene. We got sp2ch vibration there, that little shoulder, and this ch, or this carbon-carbon double bond right here at about 1,600. That's diagnostic as well. You don't see that carbon-carbon double bond thing at 1,600. You see it below 1,500, and that's for a single bond, carbon-carbon single bond. And then hexine, this one's even more diagnostic, I'd say. You see the sp2 hybridized CH, or the sp, sorry, for an alkyne, right here. And then the carbon-carbon triple bond right there at 2,200. and then all the CHs there for that. So you can easily tell these three apart, I think, just by the IR. Okay. But you use mass spec also. Well, that's another thing. I don't think I mentioned it. We always use these techniques in combination. Mass spec with IR and then with NMR, okay, to really nail down the structure. But here's an alcohol, typical, big, broad thing, 3500. Ketone here, very sharp, very strong at 1700. And then an ether, doesn't have either of those. It has a CO single bond stretch, which is buried down here around 1200. It's in this big peak here. And then the fingerprint region's complicated there. But you could easily tell these three apart, I think, just based on those frequencies. Again, carbonyl, 1700. Okay, that's an important one to keep straight. Alcohols, what did we say? 3500, very broad. Carbon hydrogen bonds around 3000. Okay. Triple bonds, 2200. Okay. Based on those, you can tell most of those apart. Here's nitrogen. Here's an amine. And we have two different modes here of the stretching. Okay. And that's a symmetrical stretch. I need to do it, sorry. And an unsymmetric stretch. Okay, so those are the two little things here for the two hydrogens coming off that nitrogen. It usually shorts up. It appears to be a little doublet. Okay, but that's not what it really is. It's two different modes of stretching. Okay. And then the CH is there. And then the amide here, big carbonyl. The amide thing, due to resonance, the carbonyl on an amide is at a lower frequency because the lone pair can be donated in and lower the bond order, the CO double bond. We'll need to go to the board and go over that maybe next time. And then here's a triple bond for the nitrile, the cyano compound right here. So you can see all the differences there, I think, of those. Compounds right here. So how would you tell these two apart? Let's see, what might these be? Let's see if I've got, this is a problem, I think, from the book here. Let's see, we got two there. One is acetone. Cullen, let's go to the board here. We got two compounds here for these two IR spectra. One, I'm going to tell you, is acetone, and one is this amino cyanide. So just examining these two structures, which one would you expect to be which? This one would be around 1700, right? Inverse centimeters. This one would be up here around 3500, but it'd be very small, okay? And then this one here would be around 22, okay? So can you tell which is which when we go back up here? Let's go back up to there. Sorry, Colin, giving you a workout. So which one is acetone? Can you tell right away? Is it A or B? Let's vote. Who says acetone is A? Okay, I think we got to. Who says acetone is B? Okay. Okay, so what made you say acetone was A? Somebody can tell us what stands out there. Yeah, the 1700 right there. Okay. And you got the CH stretches there at 3000, that's fine. And then here, B has to be what? The amino cyanide. And what stands out there? Oh, you see the little doublet for the primary amine. And then you see the big thing at 2200 for the triple bond to nitrogen. Okay. And then you don't see the 1700 thing. If it's a carbonyl, it'll be a big thing here. See a little blip there. It's a lot of little blips there, and that's because a lot of things are harmonically coupled to different vibrational modes. A lot of different modes of vibration. We're just pointing out the ones diagnostic for functional groups, okay? And then we can compare this. Yeah, we got a minute. Let's look at amides again. I just mentioned this. Let's look at the bottom here first before we get into penicillin. Penicillin's a natural product. It comes from fungi. So Alexander Fleming, maybe you've heard the story. He isolated it in the 1920s. The structure wasn't determined until the 1940s, then the synthesis in the 50s. So we can make synthetic variations of penicillin for use as antibiotics, but before we didn't know what the structure was. It has an unusual structure, this four-membered amide here called a lactam. Okay? That's the business end of the drug. So this is the drug here. Initially, they thought it was this. But yeah, let's look at amides specifically. So an amide, because of the lone pair resonance here, if you take this lone pair and draw the resonance here, you have a carbon-oxygen single bond, which is a lower bond order, which lowers the frequency, okay? So they're below 1700. They're often 1650 or even lower if there's more resonance there. Here's a typical ester, 1730. That's a carbonyl with less resonance that detracts there because what? The lone pairs are on a more electronegative oxygen. You have more of this resonance for the lone pair from the less electronegative nitrogen. And then a typical ketone there, and then a chloride, actually due to inductive withdrawal here, tightens up this bond, and it's a little higher frequency. So these are actually diagnostic right here for different carbonyls. But you see, if you're in a four-membered ring here, the resonance form would put a double bond in the ring, and that would be an even higher ring strain event. So there's less of this resonance if it's in a four-membered ring, and it jumps back up. It has more ketone-like character because of the four-membered ring. So this was really confusing initially to the scientists trying to figure out the structure here. But yeah, once it was figured out, and then the crystal structure by Dorothy Crowfoot Hodgkins, a very famous lady chemist at Cambridge in England, she figured out the X-ray structure of penicillin and confirmed all their thinking here. R.B. Woodward at Harvard figured this out based on the IR and said, no, it has to be this four-membered ring. It's not consistent with this five-membered ring. There's more details there, obviously, but the IR thing I think is good to go through. For reactions, we can use IR. Here's an alcohol. We oxidize with the chromium agents that we talked about in 12. Go to the ketone here. So we go from an OH group at 3,500, and now we have a carbonyl, a ketone here at 1,700. So just based on the IR, we can tell that that reaction is working, okay? And yeah, we'll get into this problem. We'll do this on Friday. So we'll still wrap up a little bit on IR. But we've covered all the basics of it. You can start working on the homework. It's not due until Friday there, but yeah. Mass spec and IR, very important. We'll use these in conjunction with NMR, so very good. We'll see you next time. Okay.